Welcome to this lecture series in linear algebra. In this lecture, we will discuss how the characteristic polynomial behaves with the determinant. And we will be using a lot of material from the previous lectures. So, of course, we'll need the definition of the determinant of an endomorphism. So, if T is an endomorphism on a vector space V, we saw that the definition that we gave for its determinant was that pick any basis of V, make the matrix of T with respect to this basis, take the determinant of that matrix. And we showed that this is independent of the choice of basis. So this is a well-defined object. Okay, we will use the cyclic decomposition theorem, which says that every vector space, or rather, suppose we have an endomorphism on a vector space V, then the vector space V can be written as the direct sum of cyclic subspaces with respect to T. So V can be written as the direct sum of such things. This direct sum ... V, K, T. That's the cyclic decomposition theorem. Of course, we need to know what is the meaning of cyclic subspaces, and there's a lot of theory that was used to prove this. And it won't be possible for me to recall every little fact that we are going to use. I'm assuming that you're familiar or you have digested the key concepts associated here. You do not need to know the proof of the cyclic decomposition theorem, but there were some basic things that went into the proof associated with the notion of cyclic subspaces, etc., minimal polynomials, and so on and so on. So I'm assuming you have general facility with them. Okay. We will use the notion of the characteristic polynomial. To define this, we needed the concept of algebraic multiplicity and as a consequence of the characteristic exponent. Maybe let me recall a little bit. So what was the algebraic multiplicity of an eigenpolynomial P? So we have some endomorphism on a vector space V, and suppose P is an eigenpolynomial of T, then the algebraic multiplicity of P is nothing but the dimension of the space of generalized polyeneigenvectors corresponding to P. In other words, the algebraic multiplicity of P is the dimension of the kernel of Pt to the saturation exponent. And in fact, in place of the saturation exponent, you can write the dimension of V and it won't change anything. So that was the algebraic multiplicity, and we saw that this is divisible by the degree of the eigenpolynomial, and the ratio, this ratio was defined as the characteristic exponent, and the characteristic polynomial is U product over all the eigenpolynomials. This was the characteristic polynomial, and we saw that if we write Qx to denote the characteristic polynomial, we saw that Q of T is 0. This was simply because the minimal polynomial divides the characteristic polynomial. That was all. Okay, of course, this was very quick for so many things that are happening in the background. So I'm assuming that you are well versed with these concepts. Okay, with that, let us proceed. Here are some problems for practice. This is an example where we just compute the determinant of some endomorphism. I should have discussed this in the lecture itself, but I kind of forgot to. So here is an example where you get your hands dirty, and it's very important to get your hands dirty to fully digest some mathematical concept. Okay, this is a nice problem. And lastly, this is a simple generalization of something that we saw in the lecture. Okay. So first lemma, we have an endomorphism on a vector space V, and we have some non-zero vector in the vector space. So we are assuming the vector space is non-trivial. And suppose Qx is the smallest degree monic, which kills V in this sense, right? And it is easy to see that Qx is nothing but the minimal polynomial of this endomorphism. this is a t invariant subspace, so we can restrict t to that subspace, and we can talk about its minimal polynomial then, and that is same as the smallest degree monic, which kills v. So you should be clear about this. This kind of thing we did many times earlier. Then we want to say that the determinant of this restricted endomorphism is some sign which is what is written here, times q of 0. So very interesting that the value of this polynomial at 0 is governing the determinant. Something very amazing has happened. So let's see the proof. You should pause the video and make sure you understand the statement and then proceed. And here is how we are going to prove it. So let qx be written in this fashion, x to the d, and then the coefficients. So that is, let's say, qx. And now note that, or we know that this list is a basis of this cyclic subspace. Again, make sure that this point is clear. And now, oops, what happened? Now, the matrix of this endomorphism with respect to the basis that we just talked about is this thing. So let me explain that. What is T of V? T of V is the second basis vector. So when we are developing the matrix of this guy with respect to B, the representation of T of V is 0 for the first basis vector, 1 for the second basis vector, 0, 0, 0 for the rest. And therefore we see this column where the first thing is 0, the next thing is 1, and everything below that is 0. This just means that everything in this triangle is 0. So 0, 1, and then 0, 0, 0, 0. What about the second column? For the second column, we look at the second basis vector, take its image under our endomorphism, and see what happens. Its image R endomorphism is this thing. So the matrix would then, therefore, the second column of the matrix would therefore register a 0 for the first entry, 0 for the second entry, 1 for the third entry, then 0 for the rest. So 0, 0, 1, and then all zeros. This is a 0 because when we write a big 0 here, it just means that everything in this triangle is 0. So this is how we populate the matrix up until the second to last column. So the T to the D minus 2 comma V, that basis vector maps to this guy, and hence the second to last column looks like this, all zeros and then a 1. But what about the last column? To do the last column, we look at this last basis vector, take its image under T, and register the coefficients of all the basis vectors. But what is T to the D, or rather, what is the image of this under our endomorphism? The image of this under our endomorphism is this thing. And to find out the coefficients of all the basis vectors, which are used to express this as a linear combination, we will use the fact that Qt of V is 0. So Qt of V is 0 gives that T to the dV plus AD minus 1 T to the D minus 1 V plus dot 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 is 0. So just use this expression. So the coefficient of let me maybe write that down so that it is completely clear. Yeah, so we have T to the dV is equal to minus summation, or let me not use the summation symbol, this thing that's what it is, right? Simply because Qt of V is 0, so we get that T to the D of V is all of that thing. But this minus is better we put it inside. So we have that. And therefore the coefficient of v is minus a0, which appears here. Coefficient of tv is minus a1, which appears here. And up to coefficient of this guy, which is that which appears here. So this is just how we develop the matrix of any endomorphism. I'm just illustrating or exposing a little too much here. So that's the matrix of this endomorphism with respect to our chosen basis. And therefore, this implies that the determinant of this endomorphism is, well, how do we find this determinant? We use the recursive formula for the determinant. The first row has all zeros except for the last entry. So we'll use the recursive formula for the determinant, which is also due to Laplace, I think. That is what we said. So this, we'll expand using the first row. So we'll get 0, 0, 0. We don't need to bother. Then we'll get this thing times the determinant of this particular block with an appropriate sign. Okay, but what is the sign? The sign will be minus 1 to the power d plus 1, because it's the first row and dth column, so 1 plus d, that will be the sign, times the entry, which is minus a0, and times the determinant of this thing, times the determinant of that thing, but that thing is the identity matrix. Right? That thing is the identity matrix, so its determinant is 1. So that's what it is. Very interesting. Which is equal to minus 1 to the d times a0, which is as claimed. Because a0 is q of 0. So that finishes the proof. Make sure you follow this proof in its entirety. Okay, let's move on. So we'll use the previous lemma to get a little bit more powered lemma. Again, we have an endomorphism on a vector space V. We have an eigenpolynomial of it, call it Px. And let Vp be the space of generalized polyeigenvectors corresponding to this eigenpolynomial. In other words, Vp is the kernel of P of t to the power saturation exponent. And again, to recall, the algebraic multiplicity with respect to, the algebraic multiplicity of the eigenpolynomial P is the dimension of this Vp. Doesn't matter, that is not what we are going to use, or yeah, we are actually going to use that here. So the determinant of this endomorphism, since this is a T-invariant subspace, we can talk about this endomorphism, and the determinant of that is some appropriate sign times a similar expression, P0 to the power some exponent, which is the characteristic exponent. So the characteristic exponent is, as we recalled in the beginning also, characteristic exponent is algebraic multiplicity divided by the degree of eigenpolynomial. Yeah, so make sure you understand the statement, and let's now look at the proof. Okay, so we will use the cyclic decomposition theorem. So we have Vp, which is by definition that thing, which is by cyclic decomposition theorem equal to that for some generalized polyeigenvectors, right? So we use the cyclic decomposition theorem, and let us denote this thing by Z1 and so on up to Zm, just for convenience. All right, and let dimension of Zi be written as di, which is, we know, is going to be a multiple of degree of px, something that we learned earlier. So that is going to be some ki times degree of px. So this we saw way earlier, that the dimension of any cyclic subspace, or the dimension of the cyclic subspace generated by an generated by a generalized polyengenvector corresponding to an eigenpolynomial p, is going to be divisible by the degree of the eigenpolynomial. Therefore, this equation is justified. All right. So thus, again, this is something that you need to know, that this is the smallest degree monic, such that this is 0. Again, something about cyclic subspaces. Try to prove it. If you're lost as to why this is true, try to prove it right here. It is not hard. Okay. And now by the previous lemma, we have that the determinant of T restricted to Zi is a T invariant subspace, so this is a meaningful endomorphism, is equal to -1 to the power dimension of Zi times the evaluation of the smallest degree monic that kills Vi at 0 immediately from the previous proposition. And since Vp is this direct sum decomposition, each of them are T invariant subspaces, the product of all these determinants is the determinant of T. This is in fact an exercise in today's problems. So finally, the determinant of T restricted to Vp. Yeah, so when I said the determinant of T, I should have said determinant of T restricted to Vp. So this is the product of these things, because Vp is written as direct sum decomposition of these T invariant subspaces. This is equal to the product, which is this product, but that is equal to, which is equal to, this is the dimension of Vp. So all I'm saying is that this thing is dimension of Vp, because d1 plus ... up to dm is equal to the dimension of that. This is after all a direct sum decomposition. So this is equal to that. What about this? That is equal to dimension of Vp divided by degree of A, or degree of Ps if you want. Right? Because what is di? Di is ki times degree of Px. Summing up all the di's gives us dimension of Vp. So sum of all these numbers is dimension of Vp, but this is a common factor to all of them. So basic algebra. So this is equal to that ratio. But this ratio is nothing but the characteristic exponent. Since dimension of Vp is nothing but the algebraic multiplicity of the eigenpolynomial P, we are done. This is equal to -1 to the power dimension of Vp times P0 to the power characteristic exponent. Very interesting. Okay. So now finally, this is our main theorem. Fix any endomorphism on a vector space V, and let's say this is the characteristic polynomial of T. Just to recall, Qx is nothing but this product, where this is the set of all the eigenpolynomials of T. Okay, we claim that the determinant of T is an appropriate sign depending only on the dimension of the vector space times Q of 0. So the value of the characteristic polynomial at 0 governs the determinant along with the dimension of the vector space. Okay. But also know that, one should know that the dimension of the vector space is same as the degree of the characteristic polynomial. So perhaps a better looking expression would have been that this is equal to minus 1 to the power degree of the characteristic polynomial times q0. So now we can say that if you know the characteristic polynomial of t, you know the determinant of t. That's perhaps a better way to say it. Of course, it's the same thing, but anyway. All right, so now let's prove this. It's going to be a very simple proof because we'll use the primary decomposition theorem. So let this be the set of all the eigenpolynomials of t. Right. For any eigenpolynomial, we write Vp to mean the space of generalized polyeigenvectors corresponding to that eigenpolynomial. And we know by primary decomposition theorem, V admits this direct sum decomposition, and therefore, since each of the VPs are T invariant subspaces, the determinant of T is this product, right? But by the previous proposition, this is minus 1 to the dimension of VP times P of 0 to the power characteristic exponent, which is minus 1 to the power summation dimension VP and a product overall eigenpolynomials of this quantity. But the first term is the dimension of the vector space. The second term is q of 0 by the definition of the characteristic polynomial. It's an immediate consequence of the previous proposition. Okay, now let's see some consequences of it. So this is something that we've already proven, that if we have an endomorphism on a vector space V, and we are not assuming anything about real or complex or anything, everything we did was for arbitrary fields. So then T has non-zero determinant if and only if it is invertible. Let me first give a geometric meaning to it. I forgot to do this in the previous lecture, and then I will explain as to how the previous proposition also yields this. The geometric meaning is the following. What is the determinant of an endomorphism trying to capture? We have some set of, or maybe in the R2 situation at least, let's see. We have these standard basis vectors, and T has, these two vectors are the images of them under T. The area of this guy is supposed to be the determinant of T. And it should be intuitively clear that if this area is positive, then T is going to be invertible. And if this area is 0, then T is going to be not invertible. So that is exactly what this is trying to capture in full generality. And now let us see why this follows from the previous proposition. We know that this thing is some sign which is equal to this times q of 0. Now, what is q of 0? Or before that, so the question becomes, when is this 0? This is 0 if and only if determinant T is 0. So the question is, when is this 0? But this is 0 if and only if 0 is a root of the characteristic polynomial, right? So the question is, when is 0 a root of the characteristic polynomial? But note that the roots of the characteristic polynomial are precisely the roots of the minimal polynomial of T. Because the characteristic polynomial and the minimal polynomial have exactly the same irreducible factors. So 0 is a root of T if and only if it is a root, 0 is a root of the characteristic polynomial of T if and only if 0 is a root of the minimal polynomial of T, if and only if 0 is an eigenvalue of T, if and only if 0 is not invertible. So this being non-zero just means that 0 is not a root of the minimal polynomial of t, which means 0 is not an eigenvalue of t, which means t is invertible. So this is a chain of reasoning, but it should be obvious by now. Okay, lastly, let's prove one nice fact, that determinant of an endomorphism is same as the determinant of its transpose. This is not at all obvious, but this is true, and now we can prove it using our proposition. And the main thing to note here is that the characteristic polynomial of t is same as the characteristic polynomial of the transpose of t. Now, I don't remember if I proved it in any previous lecture. So in that case, let me give a full argument, but I'm assuming you recall that the minimal polynomial of t is same as the minimal polynomial of the transpose. That I'm pretty sure I gave a proof of. Here I'm going to show that the characteristic polynomial of t is same as the characteristic polynomial of the transpose. And once we do this, you use the previous proposition and you can immediately establish that. As a consequence of this thing, you should be able to immediately prove that if you have a square matrix, then the determinant of the square matrix is same as the determinant of the transpose of that matrix. So the rows can be interchanged to columns and the determinant doesn't change. It's a very interesting fact which you can prove using the formula for the determinant, but it's better to not use the formula. It's a very soft proof that we are now developing. Okay, so let's establish this, or rather let's establish that. And why is that? So this is because t and t transpose have the same minimal polynomials, and hence the same eigenpolynomials. Also, for an eigenpolynomial p or px, we have the algebraic multiplicity of p with respect to t is, well, by definition, it is the nullity of this endomorphism. Not by definition, maybe. In the definition, perhaps we use that. I don't really remember how exactly we defined it, but we know that it is same as, instead of the saturation exponent, we can as well write the entire dimension of the vector space. And by nullity, we just mean dimension of the kernel of this guy. So the algebraic multiplicity of p is, the algebraic multiplicity of p with respect to t is this nullity, but the kernel will not change or the dimension of the kernel will not change even if we take the transpose. So that much you should know about the transpose of an endomorphism. Make sure you understand this equation. We had previously shown that if you have a linear map, not just an endomorphism, but a linear map, the rank of t is same as the rank of t transpose. But if you have an endomorphism, the nullity of t will also be equal to the nullity of the transpose, simply by the rank nullity theorem applied to what we just said. So the nullity of this is same as the nullity of the transpose, but the transpose kind of gets pulled inside. This is equal to nullity of that, but this is equal to the algebraic multiplicity of p with respect to t transpose. So the algebraic multiplicities of every eigenpolynomial are also the same, and hence the characteristic exponent are also the same. So if all the eigenpolynomials are same, all the characteristic exponents are same, the characteristic polynomials will also be the same, and that's it. Since t and t transpose have the same characteristic polynomial, they will have the same determinant. Okay? And there are some more consequences here of the previous proposition. One more consequence is the following. Suppose we have an endomorphism on a complex vector space, where V is a complex vector space. Then determinant of t is the product of all the eigenvalues of t where we multiply according to multiplicities. So all I'm saying is, if lambda 1 up to lambda n are all the eigenvalues counting multiplicities, then the determinant of t is nothing but the product of all of them. That is simply because the characteristic polynomial of t would then look like something like this. That's the characteristic polynomial of t, and lambda 1 up to lambda m are distinct eigenvalues, and k1 up to km are the saturation exponents. So q of 0 is, you'll see, it's minus 1 to the some sign, and lambda 1 times, or what am I saying? So this is q of x. Then minus 1 to the power dimension of the vector space times q of 0, you can see, is equal to lambda 1 to the k1 dot 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 lambda m to the km. That you can see because k1 plus dot 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 km is same as the dimension of v. Use that fact to just deduce that. So in case where the minimal polynomial splits over the field where we are working, the determinant of the endomorphism is product of the eigenvalues repeated according to multiplicities. So this is a nice consequence that we should have separately written out. But anyway, this is perhaps the way we stated it here is the most general, the most nicest way of looking at it. Everything else just follows. Alright, so with that I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.